All right, recording is rolling. It is Friday, December 1st. I have the starter question for you guys, tension and a cable. We can do a quick review of torque and also do a bit of coach on that. Ooh, I have the bicycle wheels out. I'll do a angular momentum demo with you guys. Talk a little bit about stability from physics definition. You guys see some foam boards around your desk, foam boards. So we'll do center mass activity and AP. You guys know AP Classroom Unit 7. Have it done before Monday, so on Monday we can go over the answers. All right. Before we go look at that cable, I want to switch over to a little bit of follow up from yesterday. Yesterday, I was talking about like the solar storm that headed our way. I said you might be able to see the northern lights. I was thinking to myself, I didn't see anything, and then I found this. Said, okay, well, yeah, you had to be like pretty far north to see that. So didn't quite make it all the way down here, but 1859 it did, but it is not 1859. Right, so here we go. All right, what's the tensionless cable? And so right before I hit record, ask you guys, Eli say he got 57 newtons, which is what I got too. And then earlier today, Gavin Lloyd got it. Yeah. So let's see, how would you do this? Well, we got a beam. I told you the beam is 10 meters long and it weighs 100 newtons, right? It looks like it's attached to this pivot point in the wall. Now maybe this pivot point is like a hinge. It would be free to rotate, except that the far end is attached to the cable, attached to the wall at a 60-degree angle from a beam, right? So 60 degrees to the horizontal, right? Right, so there'd be some tension to hold that in place, right? So this is equilibrium. Let's go back, look at the conditions for equilibrium. Equilibrium, right? So I need the sum of the forces goes to 0 newtons. Now that's in each direction. We can treat this as a two-dimensional problem, like an XY plane. So I'll say in the X direction, that's true. The sum of the forces in the Y direction is 0 newtons. Right? Now let's think about what that means for this particular setup. Right? I think this cable is pulling up and to the left. So it's kind of up and kind of to the left. You can probably do a little trigonometry with that 60-degree angle. Right? So it's kind of pushing this beam into the wall, isn't it? You guys think this beam or the wall at the hinge pivot point is like pushing back, right? With like so that those two horizontal forces zero. That's that condition right there. Okay. The cable is also kind of pulling up-ish, and I bet at the hinge point it's also partly holding the beam up, and then the beam's weight is down. That's like three forces you're considering, right? Weight down and these two, well, components of forces upward, right? That would also zero out. That's that condition. But you know what? You can actually answer this question with like ignoring those two facts, and you can solve this with just torque. Here's the third condition for equilibrium that we just added this week. The sum of the torque goes to zero. That's guys, what's the unit I'm gonna write? Zero what? Newton meters. There you go. 0 Newton meters. Right. If you wanted to go with the right-hand rule, I might call this, like R cross F, about the Z-axis out of the page. But we're just sticking to clockwise, counterclockwise, right? So it zeroes out. So those are conditions for equilibrium. I'm gonna redraw this so I can do some more work here. Right? You guys probably have this set up in your notes, and you guys saw this already. Right? Just set up. Right? There's a cable tension pulling this way. I'll call it F sub T, right? Like tension force, right? I got a 60-degree angle there. If I'm looking at all the free body diagram forces, what about the weight of the beam? I said 100 newtons. Yeah, could you think of it this way? You say, well, the weight is distributed evenly. So maybe if I divvy it into like 100 parts, it'd be like 1 Newton, 1 Newton, 1 Newton, 1 Newton, 1 Newton. And I could do it all the way across like for 100, right? You could think of it that way, right? Is it perfectly okay? And maybe from a rotational inertia point of view, you kind of want to think of it like that, right? It's distributed, right? But since we're doing a torque problem, is it perfectly okay to assume that the entire weight of the beam is acting at the center of mass, right? Which would be like the geometric center. Yeah, that's what I'm going to do. I'm going to put 100 newtons down right here. I'll say mg, the weight of the beam. It's like 100 newtons, right? And it's as if it's acting at its own center mass, right? And that's perfectly fine. It'll give us a perfectly valid answer. Okay. There is at the hinge point, I bet there's an F sub x and an F sub y also helping hold up the beam. But if I label this point the pivot point, like if I define that as a pivot, right, then that's a convenient point to pick because those unknown values now are not going to factor into torque. Because if you go like pushing on the door hinges of a door, that doesn't cause any rotation, right? Okay, so right. So relative to that point, what do we got? Right. Oh, I should split this tension into components. Shouldn't I do that? Right. That tension is trying to pull in up and kind of pull into the left. So I'll do that. I'll split those, right, those components, right? Right. Guys, is this 60 degrees right here? Right? And I could call this, I really care about this component for the torque, right? Because the parallel component doesn't actually cause any torque, right? But the perpendicular, guys, this is the tension force that we're solving for times what? Sine of 60 degrees, right? Yeah, so you guys are getting really comfortable with that by this point in this class, right? Right. Trigonometry. Okay. All right, so let's take this one condition right here for equilibrium and solve it with this one condition. The sum of torque goes to 0. That's all we need. Right? Now, I remember torque is R cross F, or R times F times sine theta, if you like. These are vectors. Right? And for equilibrium, the sum of torque goes to 0. Newton meters. Right? So sum of torque. So the sum of the R times F's. Right? So using this as my pivot point, it looks like, let's pinking this thing. The weight says let's go clockwise, and the cable is kind of pulling back counterclockwise. So that's 2 torques. Okay, so the sum of torques, there's just 2 of them. Okay. Clockwise and counterclockwise. So let's go, this radius of 5 meters is the point that the weight acts at, right? Think of it that way. 5 meters times 100 newtons, R cross F. 5 meters radius crossed with 100 newtons force. Right. Now, clockwise, I'll call that the negative direction. You usually do. If you want to define it the other way, just look at the right answer. Okay. I'm going to count counterclockwise positive. So I'll say plus, and at the full 10 meters length, 10 meters, okay, I've got this tension force times sine 60 degrees. Okay. Ft sine 60 degrees. Right? And this all is equal to 0 Newton meters. Right? We're solving for a tension force. Right? Okay. Are you guys okay with that setup? Clockwise, counterclockwise, zeros out. Okay. All right, so if I'm solving for this tension force, see, some algebra steps, tension force equals, well, here's 500 Newton meters. I'm going to add that over. So 500 Newton meters, right? And then divide down this and this, 10 meters and sine 60 degrees, right? That should do it. Okay. 500 divided by 10 sine 60. Right. Looking at, yep, 57.7 newtons. There you go. Okay. So, like if I broke this cable apart and I slipped in one of these spring scales, it's going to read probably like that right there. About 57.58 newtons. Right? You guys can do that? Torque. Torque. Oh, yeah. Torque. All right. You guys ready for our next thing? Next thing. Right, so told you guys a bit about angular momentum. So gyroscopes, figure skaters, you want to think in terms of angular momentum. I have this bike wheel. Right, so if you're watching this video at home, you have to use your imagination a little bit. I got this bicycle wheel. It's got these handles at the center. I can get this on camera. I don't know. It's kind of a tight fit there. Right? But so low friction, give this a spin. It spins really easy. Right? So I'm going to narrate this. If you're watching this video, just use your imagination a bit. Okay? If I'm holding this, it feels like a normal object, you can turn it, whatever, right? But if it gives us a rotation, give it a spin, right? Well, now the physics changes. Right? So give this thing a spin, right? You guys see how it's like it looks like it's levitating? Guys, it looks like it's levitating, right? But it's also like processing. It's processing. Okay. Let me get that a little faster spinner. Okay. So what if, and if I hold it on the other side, look, it processes the other way. Look at that. Looks like it's like levitating, right? Because it doesn't want to change its orientation because it's trying to conserve angular momentum, which is a vector, so it's trying to maintain the axis, right? If I do turn it, I feel a resistive force. It does not want to change its orientation, which is kind of hard to see. You guys get your hands on this later, so you guys get to feel this, right? But you can really see it if I step on the turntable, right? And if I turn this like 90 degrees, oh, look at that. It's like turning, like it's forced me to change direction. Okay, you guys see that? Look at there. That's pretty good right there. All right, so set that there. Later on, I got an activity. You walk around the room. At some point, get your hands on that. Give that a spin and try that out. Okay. Okay. Then, stability scenarios. Yeah, let's talk a little bit about stability. Right. Have you guys ever tried to balance a pin on your finger? Right. It's like nearly impossible. Maybe you just say like impossible. Like that's not going to happen, right? Okay. Hey, have you guys ever tried to balance a meter stick on your finger? A meter stick? Can you balance a meter stick? I think this one will work. To kind of just off camera. Yeah, look at that. Like I can hold the meter stick. Wait, why can I hold the meter stick but not the pin? What's the difference? More rotational inertia. That's what I'm looking for, right? Yeah, more rotational inertia, right? Because you think about the center mass of these things. The pin, center mass is just a few centimeters up, but the meter stick, center mass is like 50 centimeters up. Or maybe if I consider its mass distributed, I could just, what was it, like 1/3 ml squared, I think. So something to do with mr squared, right? And then like different shapes. Yeah, it's bigger radial distance. So now both of these would be unstable, like trying to balance on the end, right? But yeah, the meter stick has so much more rotational inertia, it's easier to correct any deviations and keep it upright. All right, so maybe we want to think a bit about stability. Like, what would make something stable or unstable? Like, what's the physics definitions of stable or unstable? So let's get a big old floor going. So hatch in the floor, right? And draw different scenarios. Say I got like a pin. I'm trying to balance the pin. Right now, this would definitely be unstable. But what would like define that from a physics point of view? What if you had like a pyramid shape? Maybe I'll do like a 2D cross section of a pyramid, right? Well, there's lots of stuff sitting on dust all over the place in this room. That's all just stable. It's all just sitting there, like including my picture here, right? So what makes it stable, right? Hey, what if right, you're trying to balance a pin? What if you actually get the pin to balance? Like you sit there, it's all fine and good, right? And then like little tiny air molecules move around, like little tiny vibrations, right? Anything that bumps it, it's just going to fall over, right? Now, why would it? Well, here's its center mass. If it has any deviation to the left, to the right, you guys see how its center mass would have to move downward? Ooh, right. Things want to roll downhill. Water wants to flow downhill. Yeah, things want to go from like potential to kinetic energy. Yeah, so any deviation in its motion would cause it to topple over. Versus, look at this this pyramid structure here. Here's the center mass of like this pyramid shape. Right? If you came along and like gave it a push to the right, right, wouldn't it actually rotate about this point right here? And its center mass would have to go higher, right? Or if it's sitting there, you push it to the left, it would rotate about this point, and center mass also has to raise, right? So center mass is already in the lowest position it could be. It's already in the bottom of the valley, think of it that way, right? Which is like the most stable. And it's stability, right? There's also something called neutral stability, right? Which is like if you have a ball sitting on the floor. Let's draw a ball here on here, right? So that if you came along and like push the ball, its center mass would not raise or lower. It would just, the center mass would move along that dashed line right there. Right? So that's neutral right there. Right? So let's do a couple other examples. How about a picture frame hanging on the wall? So picture frame, right? Here's the center mass of the picture, right? Maybe there's, if you could see behind, there could be like a nail, there could be a wire passing over the nail. Like that'd be pretty stable, right? Like if an earthquake comes along and like shakes this, maybe it like shakes it a little bit, but it just falls back into the original position, right? Because here's your pivot point, the point of the nail, the wire going over the nail, okay? And if you like push the picture frame, it's gonna pivot about that point. And then if you push it the other way, looks like that, right? Yeah, so center mass is already at the lowest position, hence example of stable. Right? Now my honor students, in their book, they got a real interesting question that involves a tightrope walker. Look at this tightrope walker guy, right? Tightrope. He's got that long pole, Hey, you guys ever try to like walk along something skinny like a pipe, right? And how do you bounce? Do you hold your hands out? Hold your hands out. Yeah, that helps keep you stable. Right? Why? Why does that help you balance? More rotational inertia. Yeah, more rotational inertia. Yeah. Now the way this is worded, it says, how does the pole increase the tightrope walker stability. It says, hint, consider both center of mass and moment of inertia. I think they're looking for a couple things. Yeah, I would say definitely increase moment of inertia, right? Right. So if he gets a little bit unstable, he can correct those motion really, right? They had a little bit more detail here. It said tightrope walkers often carry long poles that sag. So the ends are lower than the center. Right. Okay. So they're extending that idea. Let's see what that would look like. So like here's the tightrope. Right, here's tightrope walker. Right. Oh yeah, thanks. Let me zoom out. Okay, right. And now if you had a long pole, then yeah, definitely rotational inertia. Right. But what if you have like a saggy pole? Let's do something like this. What if it's really long and pretty massive? Okay. Hey, do you think it's possible if this is long enough and heavy enough and saggy enough that the center of mass of this whole system might actually end up possibly like below the rope, below the tightrope, right? I had to go home and think about this one last night, right? I think that's what they're getting at. Because if that were true, like if you could get that set up and this guy like loses balance and starts to fall over, think about what that would actually do to the system. Okay, like, okay, so he's falling over, the left side's falling over, but the right side's going up. And overall, wouldn't the center mass have to actually raise, right? Which he doesn't want to do. It's kind of like the picture frame. Oh, that would actually be stable to start with. Right? It's actually probably more stable there. Ooh, I think that's what it was. Okay. Right, there you go. There's some stuff on stability. Okay. Let's do a center of mass activity. You guys have a quarter page on your desk? You guys got a quarter page? Quarter page. Write your name on a quarter page. Everybody write their name on a quarter page. And let's number this 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 through 9. You guys got it. There are 9 foam boards around the room. One on each desk pod. There's 8, and here's number 9 right here. Weird shaped foam board. Like what is the center of mass of any particular object? So this is a center mass activity, and it's like multiple choice. Right? One of these dots represents the center of mass of this weird foam board. Right? Now, if it's an evenly shaped object like a square, it's like okay, well, it'd be like the geometric center, right? Or like this beam here. The center mass is again like the geometric center if it's evenly distributed, which would be like 5 meters over. Okay, so that's easy. Right? What if it's like a weird shape? How do you find center mass? I'll show you guys 3 different ways to find it. 3 different ways to find center mass. Right, one way to do it is, did I show you guys the Paul Hewitt version of this where you like hang this from, yeah, so hang from string. Right, I've got binder clips and strings. Right, now, if you hang this vertically, kind of do a demo in front of the screen, like if gravity is like down, right? The string will always hang through the center mass point. And if you clip the binder clip anywhere else, or maybe I'll do this off screen, I'll pull this in front of the camera, right? So if I clip the binder clip at some random point and I let the string hang straight down, it will always hang through the center mass, right? So right now it's hanging right there. Let me stop that, put that in front of the camera, right? So, well, okay, that's 2 points. So it could be either B or D. But if I unclip this and move it to like some other random point, like there, right? And then let me do this off screen again, do the same thing, right? The string will also hang through. Oops, gotta go on this up right. Yeah, about like that. Let's do. Right. Let's show in front of get that line done. Right. Let's do it there. Right. There's going through like A or D. Okay, so it's consistently going through the point D, right? Let me see if I can just make it go through D. Let's see. I think if I clip it right about there, it should work. Let me try that. And yeah. Right. You guys see it's only going through like the point D. Point D, right? Okay. So in front of the camera, boom, there you go, point D. Right. So that's one technique you can use to figure center mass. Another way you could do it, maybe this is like the weird way, is what if I throw this through the air and it's like spinning through the air? Yes, if it's spinning through the air, which point is it going to spin about? Yeah, about the center mass. I think that was kind of hard to see, but right. Or what if I chuck this through the air, like it goes to like a projectile, like parabola path? Well, there's only one point that would follow parabola, which is center mass, right? All the other points making like crazy correlations. Right? But probably the easiest way to find center mass, you could just do, right, now unclip all the binder clip and the string so it doesn't affect the masses thing, right? Is you could turn this upside down. It's the point that balances on your finger. So let me try that. I'm gonna turn this upside down. Okay? So I'm doing this like flying type, right? If I don't have the center mass, there's a torque and it's gonna fall over, right? But if I shift this around, okay, right there, okay, it's balanced. Okay, so got this upside down, it's balanced. Oh, flip this over, and oh, my finger is right on point. That's exactly the one point that it bounced on. There's 3 different ways to find it. Right. Oh, so the answer to number 9 is D. Number 9 is D, right? So did everybody on your quarter page write D next to number 9? You guys got number 9D? Right, you guys got that? Right. Hey, do you guys think you can find out the other 8? All right, so for rest of class, go ahead, you and your teammates, find the center mass for, well, the other 8. Turn this into the gray tray before you walk out of class. And there are a couple of bicycle wheels, so try that too. Pair up, get those stones, and see what that feels like. All right, and that's a wrap on the recorded.